time value of money. I hope now you have your a hard copy of the slides, and also I think it's important. It's quite important to have in your computer to have open your Excel or equivalent. I mean, an spreadsheet program or software. I'm going to use the Excel. I suppose you also, all of you have Excel. I'm going to open Excel. Why I'm going to open Excel? Because Excel is the main tool to analyze engineering economics projects. It offers us full range of different financial formulas we are going to learn and to use, and of course it allows us to create models, financial models of different financial formulas and different parameters and formulas, and we can change the parameters, and then we will have at the moment instantly we will have the result of the model. So it's a very good tool for simulation or for analysis. So let's start with the time value of money. What is the time value of money? The time value of money is the main part of the course, the time value of money, because as we have said before, the main factor, two main factors we have said are the engineering economics decision. The factor one is time, and the second one is uncertainty. Time is what we are going to see, and uncertainty will be reflected in the interest rate, in the return, in the risk we will be asking to any investment. So let's talk about time value of money. We are talking with this expression, TVM is time value of money, that the money over the years, the value of money changes. How does the value of money changes along the years? Because the interest rates. So that's we are going to see with simple cases, and then going to further and to more complicated cases. So, for example, you have to face a situation like this one. Take a lump sum, or take annual installments. What is a lump sum? A lump sum is an amount that you receive today, single amount that you receive today. This is what it is called in the financial world. A lump sum is a single payment received today. What is annual installments? Annual installments are periodically, probably in that case annually, payments. So we can ask ourselves, imagine we have won a lottery worth a big amount of 276 million euros. So we have been quite lucky, and we have won that lottery worth 276 million euros today. But the lottery has told us to decide if we prefer to receive today different alternatives. One option is to receive today, just for today and not more for the future, 167 millions. And the other option the lottery proposes us is to receive 276 millions, which is the lottery we will have we have won, but not today. They promise that those 276 millions will be received over 26 years at the annual payments of 10.57 million euros a year. So what do you prefer? What basis should you compare these two options? To receive today 167 or to receive 26 annual payments of 10 millions 570,000 euros? What do you prefer? I'm not sure. Have you got any preference? The students? Ignacio is here, okay. Yes. Okay, I agree with you, with your comment, Ignacio. It is true that it's better nowadays to earn this money today, although I give you a little more money in a year. Okay, I agree with you. That's the principle of having money today is worth than having in future. But what about this question? Do you prefer receiving today 167 today, or do you prefer to receive 26 payments of $10 million euros a year? I think it's not clear to decide that, but that's the kind of things we can answer with. We can answer. We are going to learn. We can answer with engineering economics. That's the options we are going to put in tables. We have here the option of a lump sum or annual installments, year 0 today, 1, 2, 3, and then until the 25, year 25. The option A is a lump sum of today receiving 167 million euros, and the other option B, is installment plan, periodic payments of $10 million every year up to next 25 years. So you will receive today one payment until the 25th year. It counts, if you count it, are 26 payments. What do you think? Have you got a method to choose? I think it's difficult, no? That's the kind of things we can solve. Let's go to think about that in the next slides. The problem is that we need to compare these options. We need to compare different flows of money, different cash flows in different times. So that is the main difference between payments, between option A and B, is that the time are different. So we need a methodology to compare the value of money at different points in time. For example, someone can say, okay, I prefer option A because I will put in a saving account the lump sum of 167 million euros. I will put in an account at 3% interest rate. So the bank will pay me a 3% of my 176 million euros. So we need to compare with that rate of 3% the option B, different payments. Because at the end, perhaps we will receive today more money with the option A than in the case of choosing the option B. So if we receive more money with the option A than from the option B, we have to decide ourselves for the option A because we receive today more money than the other option. So to make such comparison, we must be able to compare the value of money at different points of time. The second one is to have a methodology for reducing, for having a sequence of payments, different sequence in different times, to move those payments, the value of those payments at a single point of time, to compare the different alternatives. So with that basis, we will be able to make our comparison. So we need as a methodology to move the next, for example, the third year payment, the 10 million point 57 million euros we are going to receive in the year number 3. We need to move to know the equivalent amount of this 10 million euros in 3 years away. We need to know what is the value today of this 10.57 million euros. So this is the time value of money methodology, because the money has, along the time, has experienced a change of value. Why does the money change its value along the time, over the time? Because 3 things happen with money in relation with time. The first one is that money has a time value because it can earn more money over time, the earning power. We can see the earning power of money in a saving accounts. If I put today 1,000 euros, what is the earning power of that amount, of this amount in a saving accounts at 3% annually interest rate? That the next year I will have my 1,000 euros plus a 3% of that 1,000 euros, which is a total amount of 1,030 euros. So that's the earning power of money. If I am offered a different interest rate investment, for example 5%, different than 3%, I will prefer the 5, because at the end I will have in my saving accounts at 5%, I will receive 1,050 euros, which is higher than 1,030 euros. Other thing which happened with money is that we lost our purchasing power. We lost the quantity of things we can buy with our money in the next year. This economical process is what we call inflation. What is inflation? That today with 1,000 euros I can buy, imagine, 2,000 Coke cans at 50 cents per can. So how many Coke can I buy next year? If the inflation rate is 3.0, how many Cokes can I buy in the next year with the same 1,000 euros? I will buy a 3% less units of Coke. So in the case of the price will increase, for example, at 3% will be something like 52 cent euros. So I will have not 2,000 Cokes, I will have probably 1,940 Cokes less. So that process is a time process which is related with the increase of the cost of life over the time, and this is the inflation. And how do we measure the time value of money? We measure it in terms of interest rate. The earning power of money is measured with the interest rate. As we have said, the saving accounts gives you a 3% annual interest rate. That earning power is measured with the interest rate. So what is the interest rate? Is the cost, depend on who is in which side we are, think about a bank. We are here in a bank. We are bankers. We work in a bank, or we are owners of the bank, or in the case we are citizen or businessmen asking for money. We will see that for us is a price or for us is a cost. Okay, so let's think, for example, in the case of ourselves, we want to buy a new car, and we need 3,000 euros to help us to buy our new car. So what we are going to the bank and asking them for money. And then you ask, okay, so can you give me please the cost of having this loan? Loan is the money you can borrow from a bank, is a loan. And for me it's a cost, of course, no? And for the bank is the price they sell. So they will say, okay, so the price I'm selling money, the banks will say, the price I'm selling money is the interest rate I'm charging any loan. Today is 8%. So the bank every year will charge to us, we are the borrower, they are the lender, and the borrower, we are the borrower. The bank, the lender, will charge every year 8% of the amount we have borrowed from the bank. What is expected for the bank is at that price they are lending money of 8%. This price, 8%, generates profits or earnings for them. So if they are obtaining money, the bank is obtaining money at, for example, 7%, and they buy this money to us at 8%, they have a margin of 1%, which is the price they ask for, which is 8, minus the cost of money for them. They have lended money, they have borrowed money, at 7%. So that is the profit of lender. And this is the business of banks. And the business of bank is lending money and borrowing money, and the price and the cost of this money is the interest rate, and the interest rate is also the cost for us, and the earnings for the lenders, of course. Okay, so and we are going to continue with the concept of time value of money. We have defined what is the interest rate, and then what are the elements of any financial transaction involving interest. So any financial transaction includes includes the next elements. First one is the initial amount of money invested or borrowed in a transaction. What we call in the financial world, this is the principal. We will call with the capital letter P. The principal is the amount, the initial amount we are investing, of if we are taking money from the bank, we are borrowing the money. So that's the principal. What we are going to see is the cash flows associated with this principal. In the case of an investment, this cash flow, this principal, will generate future cash flows related with the asset we have invested with the principal. Revenues related with revenues, or cash flows related with expenses, with cost. And in the case of borrowed money, the principal will must be returned to the lender in monthly payment or yearly payments, and that those cash flows are what we are going to analyze. Second element of any financial transaction is the interest rate. We have talked about it. The interest rate, it measures the cost of or price of money, as we have talked before, and is expressed as a percentage for period of time. So, for example, we say that the interest rate is 3% per year, or is 0.5 per month, or something like that, or per quarter, or so on. Next element of any financial transaction is the time period. The time period, I'm going to see the next one. The time period of the transaction duration is the number of periods of the transaction duration. So we say, for example, we have a loan of 10 years. It means that during 10 years we will be borrowing money and owing money to the bank. Or, for example, if we are investing in a 20 years network, life network, we will have that the number of periods is 20. Or, for example, in a saving accounts, we give our money to a bank in a saving banks for a year. So this is the number of year will be 1. And another thing is important is when do we pay the interest payments. So in relation with the amount, with the principal we have borrowed or we have invested, that interest rate, the interest rate will be paid every interest period. It means that, for example, we have an interest rate expressed in terms of years, but the interest period, the payments, the interest payments are monthly, as is usually we often find in the case of mortgage, of loans for buying houses, that the interest rate is annual, but the interest period, the period of times we pay are monthly. So the interest period we will call N, and it determines how frequently interest is calculated. This is a misprint. This is small I in the lowercase, Usually I in lowercase is expressed in terms of annual rate. Okay, we have then the number of interest periods we have talked before, and then we have a plan for receipts or disbursement cash flows of every year of every period of time. This plan for receipt is money that come into account or to the project or revenues, and disbursement is money going out from the project, from the investment. And that plan is what we call is a particular pattern of cash flow over time. Another important element of any financial transaction is the future amount of money. We call it F. What is the future amount of money? But we call it this is the results from the cumulative effects of the interest rate over a number of interest periods. It means that if we put today the principal money in a saving accounts, and we are paid every interest period an interest rate, at the end of 1 year, we will have the future amount of money, would be the principal, our 1,000, and also the interest payment we have received for our money every month. For example, we will have the future amount of money of the principal in today of 1,000 at 3% annual rate, will be the future amount of money, F, will be 1,030 euros. So those elements we will find in any kind of financial transaction, from the more simple to the more complex. We will see always those elements: the principal amount, the interest rate, the interest period, the number of interest periods, the plan for receipts or disbursements, and the future amount of money. Some equivalent terms we are going to use, for example, cash flows are different, that positive are cash inflows, and the negative exit from the cash outflows. Also is synonymous is inlays, cash inlays, and cash outlays. Is also synonymous cash receipts, cash disbursement. In case of interest, we sometimes say interest rate, we say sometimes yield or discount factor. All the same is the interest rate. And also we call the term or the duration of an investment. For example, a project with a long life, with a life of 10 years, the term of the investment is 10 years, and the duration of the project, the duration of the investment is also 10 years. Let's think about the cash flow transaction among the parties acting in a loan. A loan and the repayment of that loan. We have borrowed money from the bank, so we will have receipts, we will have money, we will receive money. That's the name of receipts. We will consider these receipts as positive cash flows, and then every month or every year we will pay to the bank, we will repay the loan. So as we are thinking in our case, as we have received money, this is positive. In the case of payments, we will say that those payments are negative cash flows. Usually, in case of loans, we pay for some fees. For example, 300 for the study of your if you can pay the loan, we need to make some research and to study, okay, what we call the fees for qualification, if you are eligible or not for the loan. And then every month, for example, or every year, we will pay part of the principal, we will return to the bank, part of the principal, part of the initial amount, and then also we will be paying interest generated or associated to the principal amount we have borrowed. At the end, from the point of view of us as the borrower, the cash flows are equal to, in any year, equals to cash inflows minus cash outflows. We consider cash inflows as positives, or cash outflows as negative. And then we can use a table to represent that transaction. So at the end of the year, it's what we use here, those index 0, 1, 2, 3, 4, 5. What does it mean 1 here? When I say n equals to 1, I'm saying, if we are talking about years, that today is this moment, 0. And 1 year later, the next 35, 6 or 12 months, or the next year, will be the moment 1. 2 years from now, 3 years from now, 4 years from now, 5 years from now. What is the cash flow of this transaction? We have here in positive values the cash inflows, cash inlays, as we have said before, what we call here in this slide receipts. I receive 30,000 euros from the bank. I have a loan of 30,000. The bank has said that they will lend this money at this interest rate, yearly rate, annually rate of 9%. So we have here the main parameters of the loan, which is the interest rate 9, the principal of the loan, the amount I have borrowed 30,000, and this is the term, the duration of the loan, which is 5 years. So in 5 years, I have to come back to return the 30,000 euros to return to the bank. What are going to pay? Not only the principal, I will return them the principal plus the interest. So usually, in the conventional way of calculating the payments of a loan is preferred for many people, for consumers and for business also, to pay a fixed payment, a fixed amount every year, in order to have us a very good forecast of our capacity if we will be able to pay to afford those payments. So in general, the loans are scheduled, are calculated for fixed payment along over time. So in that case, we have calculated that the payment, the annually payment is 7,712 euros every year. But the initial studies, the approval process of the bank, they charged us fees, 300 euros. So the payments we put here in negative sign, minus 300, which are the fees. And every month, every year, we will be paying 7,712 euros. And the next year, we will not be paying any fees. And the next 2 years from now, we will be paying again 7,712. And then every year, so on, until the end of the last year, the fifth year, we are going also to pay our 7,712 euros. If we if we add all these payments, the total amount of payments is 38,863. As you see, is much more than the money we borrowed, which was the amount. The principal was 30,000. So we have paid something like more than 8,800 euros from the money we have borrowed. Why is that? Because this is the business of bank. The time value of money is reflected in that 8,800 euros. That's the interest cost of not having money today for the bank and borrowing and lending the money to you. And this is the cost of having money for us. We have to pay 8,800 euros for borrowing money. So we can separate, we can disaggregate the principal return and the interest payments. We will learn later how we can calculate those amounts because they are not constant. If you add the principal and the interest for every year, you will see that this is the payment. So what changed along the life of the loan is the interest we pay and the principal we pay. In the first years, we pay much more interest than in the last years. In the case of principal, is the opposite. In the first years, we don't pay much principal, but this principal increase over the time. And at the end, we will pay 7,000 in terms of principal. So that's the cash flow. If we see here in graphs this diagram, this is quite important, quite useful to represent any financial transaction. Is using those this kind of diagrams with a timeline, horizontal timeline. We represent the moment today, the 1 year from now, 2 years from now, 3 years from now, 4 years from now, and 5 years from now. And we see here with arrows, we express with positive cash flows, with this kind of arrows is we represent the cash inflows, and here the cash outflows. So this is quite important diagrams for representing any financial transaction. So how do we calculate the interest of any transaction? There are two different methods. The first one is the simple interest. We calculate the interest of money borrowed or lended with the formula of simple interest, but there are the most used methodology is the compounded interest. What is the difference between simple interest and compounded interest? In the case of simple interest, the interests are charged just on the principal amount, on the initial sum. So the simple interest is the practice of charging an interest rate only to the initial sum, the principal amount. We are going now to see the difference. So what does it mean is that we put 1,000 euros in a bank, and they promise to pay us 3%. You will calculate the 3% of the initial sum, not of the accumulated sum we will have. What's the compounded interest formula? The practice of charging at an interest rate to an initial sum, and that's the main difference, not only to the initial sum, but also to the previously accumulated interest that has not been withdrawn. Withdrawn is the money you have withdrawn from the account. So that's the compound interest. The simple interest is the method you use. Usually, as I have said often, is the methodology banks use in our savings account. They don't accumulate interest in the case of annually, for example, savings. What happened with a saving account that you deposit an amount and you don't withdraw this money during 3 years. So you deposit today 1,000 euros, and let's go to see what happened with that money in the next 3 years. So the principal amount is 1,000 euros. The interest rate, the I is 8%. The number of interest period, uppercase N, is 3 years. So let's go to see what happened with our money in the bank account. So in the moment today, we have here the beginning balance of the account, the interest earned from the beginning balance, and the ending balance of our account. So at the moment, today, I put 1,000 euros. So at the end of the year 1, so 1 year from now, I start today with 1,000. They will give me the interest, I will earn the interest of 8% of 1,000, which is 80 euros. And then at the end, the balance, the bank balance will be 1,080 euros. What happened 2 years from now? I start the beginning of the 2 years, of the second year. I begin with 1,080 euros. And then the interest earned is 80. Why is 80 again? All the 3 years, year 1, 2, and 3, they pay me 80,000. Why they pay so only 8,000? Because this is the simple interest. So every year I will increase my money. The ending balance will be the accumulated effect of 80 euros per year. At the end of 3 years, I will have 3 years times 80. 3 years times 80 is 240. So I will have the principal amount, 1,000, and then plus 240. So the transaction can be summarized in that way. That I put 1,000 euros today, and 3 years from now, I will withdraw 1,240 euros. So we can express in terms of mathematics that the future value, the 1,240 euros, the future value of my money today, which is 1,000, is the principal amount. They promise to return my money, to give me my money back, and then the interest payment, which are the 8% of 1,000 every year, and then as I have 3 periods, see number of interest periods, which is 3, the total this add up to 1,240 euros. So we can generalize the formula of simple interest is the future value of an investment is the present value, the principal amount, plus I, which is the interest rate, times P, which is the principal. This is the interest amount I receive every year, times N, being N, the number of periods. Okay, so you can apply the formula. Let's go to see the compound interest, which is the used in the engineering economics, is that we have a savings account with reinvestment. We don't withdraw any money, so we have an amount invested and we generate interest from not only from the principal, but also for the interest generated every year. They are also entitled to generate new interest. So let's see the same transaction of principal 1,000, interest rate of 8%, and number of years, 3 years. Let's see the balance of the cash account. We start with 1,000, and then the first year we will have the same money. Interest earned will be 8% of 1,000, which is 1,080 euros. And then what happened with the next year? In the second 2 years from now, we will start with 180 euros, and the bank will apply a compounded interest. The 8% will not be calculated in reference to the 1,000, the principal amount. No. They will calculate the interest for the beginning balance of this year, of this period. So the 8% of 1,080 is 86.40 euros. So that's the main difference of interest compounded interest, that you accumulate interest over interest earned in previous period. So we saw before in the interest rate formula, in the simple interest, we generate only 80 every year. And here we generate the first year of course 80, but the next year we will be accumulating the 8% year of the interest earned every year. So next year will be 80, and 2 years from now 86, and 3 years from now 96. So at the end, the final amount I will receive from the bank after investing with compound interest of 8 will be 1,259. If we compare with the case of simple interest, I got more money from the previous example, like something like 19 euros. So what happened in the compounding process, this is important, quite important for you to understand, is like in the cycle of series of depositing and withdrawing of money every year, I put 1,000, after a year I have 1,080, and then the interest, the compounding process includes that I apply an 8% to that amount of 1,080, not to the former, to the initial amount. So I apply 8% of 1,800, and I will get 1,116. So at the end of the second year, I will start the third period, and the third period I will apply to the 1,160 euros, 8%, it implies at the end 1,259 euros. So what is the compound interest formula? Please, this formula is the holy formula for financial analysis. That the future value is the present value of money, the principal amount I have, plus the interest rate, 1 plus the interest rate, to the nth power. So today I have F0 is the principal amount. The 1 year from now I will have the future value of money in the next year will be the previous period future value, in that case was F0, multiplied by the interest rate of this period, which is 1 year, 1 plus A, and then this is the principal amount multiplied by times 1 plus the interest rate. What will happen 2 years from now? F2. The future value of money in year 2 will be the future value at the starting period, the 1 year, the end of 1 year, multiplied by the interest rate I earn in a year, which is 1 plus 3. If I put in terms of the initial amount, I will see the principal amount times brackets 1 plus A close brackets to the squared, to the second power. So that's, we can generate the formula, we can generalize, and this will be the compound interest formula, which is quite important. So you can estimate the final amount at the end of the 3 years period at 8% as 1,240 euros, applying just this formula. So that is the fundamental law of engineering economics, the compound interest. And then we have here the formula, the future value at the end of the period n. And for example, 2 years from now, the future value of my money put save it in a saving account at certain interest rate will be the amount saved, the principal amount, times this bracket, this term in brackets, which is 1 plus interest rate, to the nth power, being nth the number of periods. So that's the basic formula, the fundamental law of engineering economics. So we can practice a problem. We have a portfolio, we have investor, we are investors, and we want to buy different stocks. Stocks are shares in the stock market, and we want to invest in public engineering. When I say public, is their shares are traded in market, in public market, like IBEX in Spain or New York. Dow Jones in New York, and we are worried, we are interested in investing our money in engineering like firms. For example, we can buy Air Liquide, Arcelor, Telefónica, Siemens, Repsol, SAP, or Vinci, which are all of them civil infrastructure engineering, or companies, relation industrial, or telecom, or industrial production, or petrol, or so on. So we want to buy, for example, in Euro stocks, which is the main European stock chain. No, we want to invest 3,000 euros in those actions, in those shares, those shares. And 3 years ago we invested 3,000, and then we say today how much, what are they worth today? And we go to a web, and we know the price of the shares, and we estimate, we calculate that this portfolio is worth 4,500 euros. So we bought at 3,000 and we can sell at 4,500. So we have a net return of 1,500. So we can calculate a quite common rate figure, which is the compound annual growth rate, CAGR. This is a quite common used term in many financial analysts or even consultancies. They say the compound annual growth rate of barrel production will be 10%. What does it mean? Let's go to see what is a 40.5% of CAGR. How is it calculated, this CAGR? This is calculated, of course, with the compounded interest formula. So another question we can answer, as the first question is, what is the equivalent compounded annual growth rate we have experienced from 3 years from now to today? And then the other question we can ask, if the portfolio value continues to grow at that current pace in the next 5 years, how much this portfolio will be valued? And then this is the use of engineering economic basis. So how is it calculated, this compounded annual growth rate? So we invested 3,000. This is the P, the principal amount. 3 years later, we have today we have 4,500. The number of periods is 3. So we use the future value. In that case, is today the stock is valued 4,500 equals to the present value. In that case, is the 3 years ago value, 3,000 times brackets 1 plus. We want to know this the unknown value. The unknown value is CAGR. How many periods? And then we have to include the power. How many periods? 3. So this bracket are to the third power. And then if we clear up CAGR is equal to 14.457. So if we calculate 3 years ago, we put 3,000 euros in the portfolio, and growing that portfolio, the price of the stocks of that portfolio growing at an annual rate of 40.47%, we estimate, or we calculate today, that this is worth 4,500. And then the second question we can ask with those formulas and also with the CAGR is the portfolio value continues to grow at the current pace, so at the CAGR, how much will your portfolio be valued 5 years from now? What we have to do is that today the present value is 4,500, number of periods is 5, the interest rate equivalent is the CAGR, 14.47. What is the future value for our stock? Will be the present value, 4,500, times squared 1 plus CAGR to the fifth. Why to the fifth power? Because n is equal to 5. So our portfolio will be worth in 5 years, in the case, of course, that the growth keeps at 14% rate, our portfolio will be valued 8,845. So that is the main formula used and the main law used in engineering economics. So let's go to use Excel. I would like to have some to practice. And then you have the PDF file. The PDF files you have in the slide you have are in PDF format. And in the PowerPoint original I have, those tables you see in graph, really they are Excel tables. So I open those Excel tables. And also we can go to the Excel and then see what happened in Excel. One important thing is that I would like to clarify to everybody that we are working with the Anglo-Saxon convention system, that our point for thousands or millions, it's a comma for American or English or British. And the convention for the decimal comma we use in Europe for British and American people, that comma used in decimal is a point. So that's the reason many slides and many times you listen me, I say 0.5, 0.5 is the decimal. So the first thing to be understandable in your Excel with the work we are going to do is changing the configuration of your Excel. Unfortunately, I don't know you, but in my case, and I see in this computer, we don't have the English language package of Office. That will be, it will appear the different options, the different names and menus of Excel or any Office file will be in English. In that case, we see in Spanish, but anyway, we can change at least the idiom of the language options for decimals and so on. So as you see, I do plus in file and then options, and then in options you can see here formulas. In formulas I think no. In revision review, no. Idiom, okay. Language, no. Advanced. Ta 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 ta. Where are they? I think it's the general option. Ta, ta, ta. No. Formulas. Review. Advanced. Here. Okay. In the options of Excel Advanced, here you have here using system-based marks. So now they is activated with the European, the Spanish one. So you have to check off here to get the check here, and then this is the decimal sign. We will go in use dot. Excuse me, the point, and then for thousands we will be using comma. So when I write here 1,000, you will see here we can format that cells with decimal position and using thousands splitter. So you see here 1,000 is in written in English. It is 1,000 is 1 and then comma, thousands, and then three zeros, and then 0.00. So the decimals is with a dot, okay, a point. And then that's the main configuration you have to activate in your computer. So let me finish the class with that example. How is it calculated this, the previous compounded annual growth rate? This is the interest rate equivalent. So we have here the models. So we can see here, I'm going to, okay, to make it bigger, okay. So the present value of our portfolio was 3,000. The future value today is 4,500. The number of years is 3. You know, those numbers are parameters of the model. This is, so I type in numbers 3,000 for those are numbers, and 3. I'm going to see better. N is the number of years, 3 also. And then we don't know what is we need to know what is the interest rate, or equivalent is the compound annual growth rate. So we can write the formula, of course. So we can try to say, I know I have in my memory, this is the present value divided by, no, excuse me, the future value divided by the present value to the, I use that symbol. Do you know that symbol is applying shift and the key on the right hand of the letter P. This is like, I don't know in English what is the name of this sign. To the power of 1 divided by n. And then minus 1. Okay. As you see here, this is the formula. I expect that all of you know Excel. So I'm going to write it as a percentage, the format. Okay, so there is another way to calculate. With a direct formula, all of you know that Excel itself has financial formulas, and the formula, if we had the English version of the Excel package, as we don't have, we will see here the English formula. We are seeing the Spanish one. The English formula will be rate. We see the Spanish formula, which is tasa, equals to, we put here the number of period. The number of period is B3 is this cell. B3 is in blue. Why this is blue? Because you see here that this cell is also blue. 0, which is a parameter always you have to put in 0. B1, which is the valor actual, the actual value, present value, 3,000. You have to put in negative because we are thinking in cash flows. I invest 3,000 and then I will withdraw 4,500, so you need to put in negative. It's a cash flow convention. And then the type, you write 1, and then it's an optional parameter of estimation. And then and then it calculates for you the formula of TASA, of the compound annual growth rate. So that's the kind of things we are going to do in the next day. We will be finishing this lecture. We have next 6 slides, and we will finish those 6 slides, and then we will see also the lecture number, let me see please, the lecture number 3. So because this time value of money and the next one, economic equivalence and interest formulas for cash flow, are the most important. So we will be seeing in the next Monday, Tuesday, and the next Thursday. So thank you very much for your attendance to the class. I see here only to Ignacio. So thank you, Ignacio, for your attendance. And then I think, okay. So have a look to the slide for the next day, please, everybody, and we will see you on the next day. So I think our technical guys are managing to publish all the streaming for the next Monday, in order to have the chance of reviewing the material with the recorded session. So thank you very much. Have a nice weekend. Bye-bye. Let me summarize what we saw about this lecture last Friday. The most important thing to remember of this of the material we reviewed was what is the time value of money. So let me just remember the main slides. And this is the value of money, okay. So the most important thing to remember from the previous lesson was that the money in general, it has value over the time. So it means that our 1,000 euros today is worth 1,050 euros in the next 5 months, in the next 5 years, if we are able to find a savings account at 5%. So, excuse me, I've said 5 years, not in 1 year. So 1,000 euros today is worth, in the next year, 1 year from now, is worth 1,050 euros if we are able to find a savings account in the bank and paying for that account, for our money, at 5%. So that's the time value of money, and this is the main tool we are going to use in our course. So we saw that this the parameter we can use to measure the value of money a long time is the interest rate. The interest rate is the cost or price, depending on who is watching this rate. The interest rate is the cost or price of money over time. So a cost is for the borrower when we borrow money from the bank, a loan, or if we are the bank, we are lending money, we earn money from the money lent. So the different elements of any investment are always the same. We are going to see even in sophisticated investment, always we see we have the same parameters. The principal amount of money invested today, the principal we call, the interest rate, which is the time value of money, the cost or price of money, and it is expressed in general as a percentage per period of time. For example, 5% annually. The interest period determines how frequently interest is calculated. For example, if we have a saving accounts that is paid at 5% annually, but we can have interest paid every month. So the interest rate is different, and the interest period is not 1 year, because every month we are getting in our account the interest produced by the savings account. The number of interest periods, it means the specific length of time for the transaction. For example, I have a saving account for 1 year, so the savings account is 1 year, the number of periods. But if I have, for example, a saving account for 3 years, I cannot move that money from during those 3 years. That the number of interest periods n is equal to 3. And then also any financial investment has a plan for receipts or disbursement, what we call the cash flows. So some months or some years we will have money coming into the account, so we call receipts, or sometimes some periods of time we disburse. So what is a disburse is we pay. We use the money in account to pay expenses, and at the end of the interest periods, at the end on the time end, what we have is the future amount of money results from the cumulative effects of the interest rate over a number of interest periods. So that was the main summary in relation with the main elements. What also we saw is the different kind of interest rates. The simple interest is the interest that is charged always over the same amount. So we don't compound. What is compounded interest as different from the simple interest? The compound interest is that you obtain, you get interest from previous interest generated by your account. So an interest rate is you charge an interest rate to an initial sum and to the previously accumulated interest that has not been withdrawn. So what is the main method used in engineering economics, and always of course in the financial industry, is the compounded interest. So the simple interest is just to know, but the most common used system is the compounded interest. We saw several examples of simple interest. We saw the simple interest formula, which is the principal. The future value of any investment is the present value. The principal value I put on today in my account, and then every period you generate an interest payment from your principal, which is I times the interest rate multiplied by the principal. So every period of time you have I times P, and then if you have, as we have n periods, at the end we will have the principal amount plus the n terms of IP. Okay. So how does it work, the compound interest formula? The idea is that your initial 1,000 euros in your account, that initial amount at the end of year 1, if we have committed with our bank 3 years, savings bank with saving account with 3 years term, we put the first 1,000 euros, and then next year at the end the bank will pay us, will pay in the account the 8%. We are now using the interest rate of 8% annually. So at the end, we will have 80 euros in our account. So the beginning balance of our account in year 1 was 1,000 plus 80,000. It means that the ending balance of the cash account is 1,080 euros. So what happened in second year, that we apply the interest rate of 8, we apply to the initial amount of the year 2, which is 1,080 euros. And then the interest earned for this beginning balance amount is higher than the previous period, which was 80. Now we have 86.40. So at the end of the 3 years period, our 1,000 euros is converted into 1,259 euros. So if we had that amount in an interest, conventional interest, simple interest rate, that amount will be at the end 1,240 euros. And now we have 1,259. So we have close to 20 euros more. So the used formula is the compound interest. So we have here, we saw the interest period, how does it work? And then this is the compound interest formula, and this is the future value of any investment is the principal times bracket 1 plus a to the nth power, being nth the number of periods of the investment. So this is the fundamental law of engineering economy, which is the compound interest formula, future value equals to principal or present value times bracket 1 plus a to the nth power. So that's a summary of what we saw. We were practicing using that formula to know the common parameter used in engineering or in other many market analysis in many circumstances is the compound annual growth rate, which is like an interest rate. The compound annual growth rate is what happened if I invested 3,000 euros in year 0 today, and then I get in tomorrow or 3 years later 450 and 500 euros. What is the average interest rate? What is the compound annual growth rate? So it can be calculated with this formula, and in this case A is the CAGR. So what we ended the lesson was with the configuration of your Excel. So from now we have several methods to calculate any engineering economics calculation. We have several options. One is, of course, with formulas, with your pen, and okay. Another is using a financial calculator. We are going to see later. Another one, and then I suggest you to use is the Excel. I mean Excel or any spreadsheet program, like for example Google Drive or so on. So the most important thing is that as we are using English language is to the configuration of our Excel to be compatible with the Anglo-Saxon units. So as you know, Anglo-Saxon language, English language, they use the decimal is not as comma we use in Spain or in Europe. They use for decimal, they use the point, and for thousands units, we in Spain or Europe you use the point, and then they use in England or in America they use the comma. So what is our Excel is configured for with the system configuration. I'm going to repeat how to change. So you go to your Excel or equivalent Excel spreadsheet, and then you go to options, and then in options you will see general, formulas, and revision, and advanced. I think is advanced here. In advanced We have here addition options, and then 1, 2, 3, 4, 5. Okay, so we see here use system brackets or system signs. So what we are going to use is not to use the system. The system will be, if your Windows is configured for Spanish language, the system will be point for thousands and comma for decimals. So we are going to uncheck this box, and so as you are seeing here now, the decimals are point and the thousands are comma. So my Excel now is configured for English. So I hope your Excel is the same. Is to uncheck the this box, to uncheck, and to put white, this square, black or white, without any check, and then put in here decimal with a point and thousand with a comma. And then if we want to calculate this problem of the compound annual growth rate, which was we were seeing, we have the formula. So the formula is using the future value is equal to 4,500 euros equals to the present value you are investing in those shares is 3,000 euros, 1 plus the compound annual growth rate, which is similar to the interest rate, to the annual interest rate, to the third power, because your investment of 3,000 euros has produced at the end of 3 years, has produced 4,500 euros. So what is the value of I of CAGR, which is the same? You can clear up this amount from this formula. The other method is using Excel. So we are going to use Excel in order that first time to have you some practice in that. So what I'm going to do is creating that Excel. So let me see the numbers. So please, you can do with me in your computer, meanwhile I'm doing. So we have here, you see, okay. So P, which is the present value, equals to 3,000 euros is the amount we are now. So you can configure the number 3,000. You can use here, for example, as euros and using 2 decimals. So the category of format of number is money, no? It's currency. And then the future value is equal to 4,500. So I'm going to use the same format. As you know, you can catch this format from the previous cell we have formatted, and then to catch with the brush, with deep brush, and then apply to the cell you want to use the same format. And then we know that the number of periods and the term of the investment is 3 years. So we know also, and then what we don't know, what we have to know is the compound annual growth rate. This is the unknown variable for us. So we have 2 options in Excel using financial formulas else Excel has by its own. We are going to see later, but we are going to create the formula, no? As you remember, P is equal to, F is equal to P times bracket 1 plus CAGR to the nth power. So if we clear up CAGR, we will see, I know in my memory, that this is the future value divided by the present value, close bracket, to the power you use the shift key and then you use the circumflex accent, which is close to the P, the people from people. And then you touch that key. You don't see nothing in your screen, but later when I write the next key, it will appear that circumflex accent. So I will use a bracket. Okay, you see now here the circumflex accent to the 1 divided by n. In that case, n is 3. So I'm going to use the Excel relative reference, and then this is minus 1. So as you see here, and then I'm going to format it as a percentage, 14.47%. So that's the way to solve. Okay. Another way is to calculate compound annual growth rate using Excel financial formulas. We see here, this is Excel. I suppose all of you know Excel, the basis, and perhaps you don't know the formulas. As you know, formulas, Excel has in it by its own, it has formulas of different kind of formulas. You see here insert function, and then you see here a category of function, what they call the library of functions. One is the financials, and then you see here, this is, of course, if we're using language, English language, or Microsoft Office, we will see here the formulas in English. This is not the case. We are seeing in our language, in Spanish, so don't worry about that. So there is a financial formula. All of these financial formulas from Excel are related with engineering economics. So I tell you that the formula we are going to use is what we call the tasa, interest rate. Tasa is rate. In English, that word in the English version of Office, you will see here this financial formula, name it rate. Okay, we use tasa, which is the Spanish name, and then you put here the number of periods, as you see, n period, and then you click here, and in this icon you are going, and then you are going, if I click here, to the Excel file you see here. Okay, so it is becomes smaller, that window, and then you can click. It is expecting for the end, so I click here, and then I come back again to the window, and then, okay, as you see, and what is the payment? The payment in that case is 0, because we don't have any periodic payment. We will see that this rate formula, this tasa formula, is quite general, and you can use for many different purposes, and by now payment, pago, is 0. We will see when we don't use 0 for that amount. Now it's 0. What is the value? The VA is the actual value, so the present value, and then again we go to we click here in the icon, and then go to the Excel, and then this is the present value. I click here, the C2 you see here, and then what is the future value? The future value is this one. You can do without clicking here, going directly to this, and then the type you use always 0, because we are calculating all at the end of periods, so always we will use here in type 0, and then you click. Oh, I'm sorry, SQL, something they don't like. Payment 0, 0, 0, 0. Okay, so estimate 0. And then what happens? C4, number of period 3, payment 0, actual value C2, future value is C3, okay, and then type you can ask for help here. If you click in the name of the formula in TASA, you click and then you go to the help of TASA. So TASA, number of period, payment, dun. I don't know what is here. Let me please, I'm going to see here. Okay, okay, so that's the kind of things that until you don't touch with your hands the problem, you don't remember. So please, let me see what is happening now. As you see here, that we are using the number of periods, which is right, 0, which is the payment is right, C2 is the present value is right, but what is expected by this formula is that we invest that present value, the C2, the 3,000 present value, and is expecting that at the end, the future value we withdraw from the account. So as we are considering the signs of cash flows, any investment is positive, and then at the end of this investment, you withdraw this money from the account. So you have to, it's a cash flow, negative cash flow. So we have to put here a negative sign, a minus, a negative sign, and then, okay, so that was the reason. And then you will remember. And then, okay, so we have here our 14. So please remember that one of the amount you are using in this formula, either the C2 or either the C3, one of them must be with a negative sign in order to have right cash flows. So as you see, you can get the same result using the formula, your own formula, or using the Excel file, Excel function. So that's have you got any question about that? Have you tried to do it in your... Okay, good morning, Alejandra, hello. Carmen is there. I don't know if just me here. You with a lot of echo. Beatriz, Juan. No? No? Beatriz is... it's fine now. Okay, thank you. Beatriz, it's fine now. Okay, thank you, Juan. Have you got any question, Maria, Beatriz, or it's fine? Okay, thank you, Beatriz. Alejandra or Maria, have you got any question about the problem we have done? Do you know how to use the Excel to configure it and then also to calculate and to know the importance of the signs of the formula? Okay, so we can proceed and we can go ahead. And then another question we can, a practice problem, we can propose this statement. If you deposit 100 euros today, this is the time n equals 0, and 200 euros 2 years from now, this is the time n equals to 2, in a savings account that pays 4.5 interest rate every year, how much would you have at the end of year 10? So 10 years from now, n equals to 10, how much money will you have? Can you try to do it by yourself? Okay, so let's see what's the answer. This is the cash flow diagram. We have today 100 euros in a savings account, so we put this as negative. We give money to the bank account, to the bank. And then 2 years from now, the n equals to 2, we deposit 200 euros in our account. Also, this is negative. And then after 10 years from now, what is the future value of our money if we have 4.5% compounded annually. So what we are going to use is a linear function, so we can calculate the future value using the general formula of compounded interest for the first deposit of 100 with n equals to from 10 minus 0 is the number of periods is 10, and the other investment, the present value of in n equals to 2 is 200, and then how many periods of time should we have to use for the compounded interest. So 10 minus 2, which is equal to 8 time periods from n equals to 2 to n equals to 10. And then we calculate the future value of deposit number 0 is 100 times brackets 1 plus the interest rate, which is 0.045 to the 10th power, n equals to 10. This is 155.30 euros. The second deposit you do in year 2 is 200 times the bracket with 1 plus the interest rate to the nth power. What is the nth power? Now is the number of period, number of periods of time, which is 10 less 2. The number is 8 years. So this is 284.22 euros. So you can sum, you can add both amounts. If F0 plus F1, this is equal to 439.72 euros. So that's the way to solve. We can use Excel. Also, we can see a cash flow, detailed cash flow. We have here the end of year in that column. We have here the 3 different columns for the investment 0, for the deposit number 0, which is 100 euros in the moment today. And we see here the 3 other columns for the second deposit, which is in n equals to 2 at the end of the time n equals to 2, you deposit in your account 200 euros. And then you see the last 3 columns, the sum of every column. So the beginning balance of each the 0 plus 1 deposit. So this is this column plus this other column. And then you see here how your money, we have seen in a previous example how is your account compounding interest. So as you say, your first 100 euros, and the next year, the first 1 year from now, 4.5 euros, and then you will get at the end of the year 1, you have 104.50 euros. Then this is compounded with 4.5 percentage. This is higher and interest earned than the previous period. Now you have 4.70 euros more, which is more than the previous period. So at the end of 10 years, you will have 155.30 euros, which is the same amount. You can calculate with the general formula. You can create here the detailed balance of your account, and then you do also it with the same with the second deposit of 200 in year 2. And then you have the same payment of interest earned, 4.5%, and then at the end of 8 years more, you will have 284.42 euros, and then you sum up, and then that's the same rule. Another solution is using Excel. We are going to see later. We can do it. So we have applying the general formula. This is one option. Second is detailed cash flow calculation. Second option. And third option is to use Excel directly. We are going to see now how is it constructed, this one. I have in my PowerPoint, you in your PDF, you don't have the Excel files inside. So if you click in your PDF table, you will not see nothing. What I suggest you is trying to do it by your own using Excel. So I have here, in order to, okay, so let me zoom that one, okay. Okay, so I'm not sure if you are going to see, okay. Here. So, what I have here is an Excel formula with the interest rate for both deposit is the same, 4.5. So as you see here, I write here in the cell B1, I write 4.5%, and then the cell for deposit 1 is linked, is equal to the B1. So in order, if I change here, I write here 3%. At the same time, the interest rate for the second deposit will change. So that's the main usefulness of Excel. So I'm going to recover, okay? And then I write here the deposit number 0 and the deposit 100, the second deposit 200. Number of periods 10 years, for deposit 1, for deposit 2, 8 years. So what's the future value? I can calculate with another important Excel formula. I'm going to explain you. The same as we have used the financial formula of tasa, of rate. We have the formula, in English will be future value. In Spanish is valor futuro. In English will be future value. This formula, future value, also has the same parameters of the previous one. Different, of course, but always we are using the same parameters. Always we are handling the present, the future, the interest rate, the number of periods, and the periodic payments. So, depending on the problems, you will feed this formula with the right data. In that case, for future value of an investment, the Excel formula asks us about the rate. So what we use here for rate is B1. B1 is this cell, the 40.5. And then they ask, the formula asks us about the number of periods. In that case, in the formula for deposit 0 is N0, this one, the cell B3. And then the payment, always as before, the previous example is 0. And then the the present value of the investment, the amount we are depositing is the cell B2, 100 euros. And then the type of calculation is 1, always 1. And then you press enter, and then you have that the future value of this amount is 155. Using the same formula for deposit 2 is the 1, in that case is the rate, the 1, this one. The number of period is the 3, which is 8, this one. 0 for payment, D2, which is the present value, 200. The deposit we are going, and then 1 as always. So you have here the formula, and then in this summarizing the result is F, the future value of our investment is future value of deposit 1, future value plus future value of deposit 2, which is equal, and then you see here the formula, B4 plus D4, B4 plus D4, okay? So I'm spending some time trying to explain this, because at the end everything will be like more or less complex, but the methodology will be the same. So have you got any question? Everything okay? No, thank you. Okay, everything okay. So if you have any question, Alejandro, María Carmen, or María Beatriz, please Don't hesitate to do it. Okay. So as you see, there are several options for solving problems by direct formula with your pens. Then always is important to draw the cash flow diagram, to catch and to write the parameters, and to have a clear view of what formula we are going to use. You have also the detailed cash flow here. It's another option, also, of course, with Excel. And then you see here the option of using directly the Excel formulas. Another past cash flow problem, another practice. Consider the following sequence of deposits and withdrawal. Deposit is putting money in your account, and withdrawal of your account is having money from your account, going to the automatic teller machine, the ATM, and to get some cash from your credit card. And then we have several cash flows over a period of 4 years. This is a misprint. As you see here, the cash flow diagram, this is not 10, it's 4. Sorry. If you earn a 4.5% interest, what would be the balance at the end of 4 years? N equals to 4. So you deposit today 1,000 euros. Next year you deposit 2,000 euros. 2 years from now you withdraw 900 euros, and then 3 years from now you deposit another 2,500 euros. So at the end of the 4 year, what will be the money will you have in your investment in your savings account? So the payment is the interest rate is 4.5% interest. We know. You should know. You have to know that the result will be. In general, not the detailed calculation we can do later. What we are going to use is moving that amount, 1,000, with that interest rate for 4 years. So will be 1,000 times brackets 1 plus 4.5% to the which power? To the nth power, which is in this case n equals to 4, because we are in today. What will be the future value of the second deposit in 1 year from now? 2,000 euros will be equals to 2,000 times bracket 1 plus interest rate 4.58% to the which power? In that case, the term is 4, and then we are here in year 1, so 4 minus 1 is to the third power. And then we are going, in that case, this one as negative calculation, negative cash flows, and then we are seeing here minus. Okay, you can have any convention, but you must be coherent with your signs. And then we have here a withdrawal of 900. So what's the future value of this withdrawal? Is 900 times bracket plus 1 plus for interest rate to the which power? Okay, so we have n equals and the term is 4, and then we now it's a second year investment, so 4 minus 2 is to the second power, and then for the third year deposit is 2,500 and 500 euros times bracket 1 plus interest rate to the 4 minus 3 to the 1 power. So that's the result, and then we will sum the P0, P1, P3 amount, future amounts, and we will subtract from P2. So that's the general idea. You can have here a detailed calculation of what happened with your account. And okay, so that's doesn't matter, you can review for yourself, and finding that the final value is of 1,000, 2,000 and 2,000, 2,500, at the end and withdrawing making a withdrawal of 900, you will get after 4 years 5,104.5 euros. So you can here, you also here have the Excel formulas. In that case, you see here the interest rate, the present value, the number of periods, and then the future value formula is the same always. B2 is the interest rate, B4, which is the number of period. In that case, for the first deposit is 4 years. The payment is zero for this note for this investment, and the actual the present value is B3, which is the amount I'm depositing today, 1,000. So for example, for the second deposit, you see here that the number of period is 3, and then for the third year, no, the second year withdrawal of 900 euros, and then we use the minus sign before the formula of future value, and then we sum up, we add up all this amount, and then we are obtaining the same result, 5,104 euros. So as you see, this is quite repetitive calculation, always using the same formula. We have used here the Excel formulas. I have explained it. There is another methodology, which is obtaining the cash flows. In that case, I'm using the time scale is in horizontal, not in vertical, and then we write here as positive the cash flows. Positive we call the cash inflows. In year 0 today 1,000, year 1 2,000, and then in year 3 2,500. The cash flows is the withdrawals of money in the second year minus 900, and then you calculate here the cash flow every year. This is the net cash flow every year, and then you estimate the future value of any cash flow of any year. So in that case, we have here for year 0, what is the future value of cash flow in year 0? 1,000 is 1,193, then and so on. So you get always the same formula. And then that's the end of time value of money. So have you got any question? My students? No? So I think, no, okay, thank you, Maria Carmen. Diana is also new. Okay, so I think it could be good for us to have a break. It's now 5 to 1, so we can have a break of 5 minutes, and then starting at 1 o'clock and seeing the lecture number 3, economic equivalence of different cash flows, which is my target to see today, and part of the number 4 lecture. So okay, so we have a question from Diana. Diana, I suppose you were not before. Oh, yes, no. Perhaps when I explain it, no, it's here, Diana, okay. So, Diana, the reason of putting, you mean before future value. In that formula, we are using here, for example, in that example, this is the slide number 26, page 26. You see here that the future value of the P2 cash flow, which is a withdrawal of money. So you went to the bank and you are going to your bank and getting some money from your account. So you are withdrawing money from your account. So you, with our convention, putting your money in your account is depositing it. So cash flow positives. these ones, and when you withdraw money, you get money from your account. This is negative one. And then when you are writing, as the future value is the sum, the algebraic sum of all the future value, the arithmetic one, you will use the arithmetic sign. So for the convention is that for deposits we are using the positive sign, and for withdrawal we are using the negative sign. So I think in that sense, when you see here the formula is the in order to be coherent with the cash flow signs we are using. So you put here a minus. Is that okay, Diana? Oh, okay. Thank you, Diana. When you calculate, there is a question from Beatriz. Thank you, Diana. Beatriz asks about when you calculate the future value of deposit 2, do you also put minus 900? Good question. Okay, so let's see how is it the problem. Yes. It is a convention. So Alejandra, Beatriz, what I suggest to you is use your own signs, but being coherent with them. So in my case, as I'm using here cash flows, for me positive cash flows are deposits, P0, P1, and P3, and for me cash flows are negatives when we withdraw money. So in P2, this is minus. So, and then when I write the formula for calculating the future value of P2, what I'm using is, as you see here, you see in all the formulas, as I said before, the Excel, what does Excel, what does Excel do is that one. So for Excel, the future formula, for example, if I say, what is the future value, in Spanish, VF, of this rate, the interest rate of 14, for a number of periods equals to 3, a payment 0, note, and actual value, present value 3000, type 1. If I use for present value the positive sign as I'm using here, I don't write a minus, the result of future value will be negative, because it's coherent with any investment that you put today a present value of money, 3000, and then the Excel interprets, or the Excel think that the future value you are going to get your money from that investment, and you withdraw this money from an account, for example. So the result of future value formula is negative. As you see here, I write here, and then you see here the negative sign. Why? Because it intends, Excel intends, that you are investing today 3,000 euros, depositing your money in your saving accounts, and at the end of 3 years, you will be withdrawing that amount from your account. So the Excel function, the future value function, use by default the minus sign as its result. So to be coherent, depends on your calculation. You want to say that this is a positive amount, so you have 3,000 today, you will have in 3 years from now 4,500. So I think it doesn't matter, depends on what are you interpreting of the result, but you must be coherent for your results. It's the same effect that instead of putting here the minus sign in front of the formula of future value, I can write the minus sign in the actual value, in the present value. So instead of using positive number for the present value, which is in the formula, I write, for example, minus. And then the result of value of VF function, financial function, will be a positive one. You see? So you have many options to handle the signs. Is that, Beatriz, that explain what we asked, Beatriz? So the most important fact is that you must be coherent with your algebra you are using. So you are using cash inflows for deposits and positive. Yes, okay, thank you, Beatriz. So we can have now the break.